Good afternoon, and welcome to today's electronic design webcast. Our topic today, how to properly test a high current FPGA power distribution network. Sponsored by Programalog. I'm Bill Wong, Senior Content Director with Endeavor's Design and Engineering Group. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, simply type your issue into the Ask a Question box. A member of our team will assist you. You can also click on the question mark help button in the upper right corner of the screen. Additionally, we welcome your questions during today's event. We'll answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, type your question into the Ask a Question box and click on the Send button. Also, please be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. Now let's meet today's speaker. Roger Beeston is experienced in systems design, field applications engineer, business executive professional career for 24 years, starting at 3D Labs, National Semiconductor, Impedance, Altera, and now Programalog. Now let me turn things over to our presenter. Roger, the floor is yours.
Thanks, Bill. Appreciate the intro. Welcome, everybody. I'm going to run through the agenda in a minute, but just before we do that, we do have quite a lot of people on the call. So as Bill alludes to, please put your questions in as they propagate through your mind. As there are quite a lot of people on the call today, I'm expecting we're going to have to sort of thread the needle with the material. So it's quite likely that you're going to have questions after the webinar as you kind of noodle on the challenges and the solutions that we're providing in this material today. So long story short, drop us a note at any time. Because we'd love to hear your feedback, and our product is based on what our customers need, so we always welcome any feedback. Okay, so I'm going to cut onto the agenda, and the first few slides we're going to talk about the problem statement. Is it a problem statement? It's a set of challenges that we need to address to take on this new set of devices that are now in the market, whether it be from Xilinx or anybody with a high-density ASIC, digital ASIC. These new chips present new challenges in terms of power delivery, as they're expected to do more. So we will run through the problem statements or the challenges associated with testing these new devices for the power delivery or power distribution network. We're going to go to my colleague in the lab, who's going to do a GUI demonstration. Do a real live test of a device. It will be a cut down version in the interest of time. We'll be discussing some of the equipment used and the results from that testing. And then we're going to go back to myself and Bill and address any questions that hopefully come through during the course of this presentation. Okay, so let's talk about the problem statements or the challenges that are presented. And I've summarized it. I've tried to summarize it into about 5 different challenges. It's probably a few more, it depends on, but these are sort of like the ones that I feel like are the most pertinent for the conversation today. So with the latest generation of FPGA device, the trend is to add artificial intelligence compute units or any other kind of sort of discrete compute units to a large digital ASIC. Really provides more functionality, but it also provides more challenges. And one of which is, especially with an FPGA, right? FPGAs are a function of the Verilog that is written and the application that the Verilog is written for. So we've got these fabulous new chips that have to be programmed. But how do we know what the load profile looks like when in this slide you can see that there's 6 different applications right there? And we know that with an FPGA, then they have the broadest set of applications. So how do we know what that load profile looks like? And that's going to be have to be a conversation between the system engineer and the person that's writing the Verilog. Maybe they're the same people, maybe it's a huge team. But the point is, different applications on the same chip. So it can't just be boxed into a certain known profile. So we have to think about what that profile is going to look like. And of course, with an FPGA, you can change, the fabric can change. You know, these things are field upgradable. So how do we take that into account as well? The short answer is lots of testing. Okay, so second problem statement here, or challenge, shall we say, is increased current. And anybody who's been in the industry for more than a few years knows that these devices, digital ASICs, you know, they take advantage of the latest geometry, which means that we get more computational power per unit area. And but at the same time, you know, there's a requirement for more power to be consumed in the device because the power per unit area goes up as well. So that means more juice into the target device. Right here, we have a slide that we basically used the Xilinx PDM calculator to, and we just ran some, put some basic tests into, so basically see how much power, what the variability is with the power. And this is peak power, but also, you know, peak can be continuous as well, right? I mean, depends what the Verilog's going to do. It sort of points to a previous slide on the profile. So we've got lots of different profiles we have to take into account. Increased power and increased current as the voltage goes down naturally as the process shrinks for every generation of device. So this really is the next slide talking about, I call this kind of the more power Igor slide really, but basically, you know, we need more current going into these devices to meet the requirements of the computation that's going to happen through the digital logic and of course the transceiver logic. But it's a known, the rule of thumb, what I've always used is for every 25 amps of power that you need delivering into a chip, or 25 to 35 amps. So I kind of like averaged it out and said, let's go halves on it and split the difference, called it 30 amps. For every 30 amps of power or current you need into a device, you need to add a phase. So this is known good technology, right? Lots of power management vendors do this. This is how we add more power to a power supply to provide more continuous or instantaneous power. We add another phase. And lots of, there's a vast majority, a lot of manufacturers that do this, right? They have multi-phase technologies, and the manufacturers can provide, whether it's a discrete solution or a module or combination thereof. You know, you could have a discrete controller, but power stages, etc., which are integrated. But the phase is going to be a power stage and an inductor. And every time we need more current, we need to add a phase. So in the previous slide, I think we calculated, let me just bounce back. Yeah, we looked at around, it looks to be peaking just north of 200 amps. And that's what the PDM told us. But we need to design a power management solution for greater than 200 amps because we want some design margin, and we need to be able to test, you know, we need to set an OCP that's higher than the worst case current event. So we need to, let's call it, I kind of rounded this up, so I added some margins. So let's say there's 270 amps peak. We're going to design a PDM for 270 amps continuous or peak. So we divide 270 by 30 amps and we get like 9 phases. So 9 phases, that's an additional, essentially 9 permutations, okay, of power that we have to, of testing that we have to do. Remember, these guys, the power management solution is running at a completely different clock domain than the chip, right? They're not synchronized to each other. It's not synchronized. So if you ever tested a power management solution, you can hit it with a pulse, and once in every few hundred or 50 pulses, you'll get a big old glitch. And it's not actually a glitch. It's probably the worst case situation where, because you've hit a pulse, you've done a transient load test on your power management device, but you've caught it at its moment of weakness. Now, the moment of weakness is those points increase as you add phases. So there's lots to think about here. especially with non-linearities with these multi-phase solutions, as every vendor who makes a power management solution has their own proprietary architecture. And these architectures are very sophisticated. They require have a lot of firmware, a lot of hysteresis, non-linearities, time constants, and firmware. And there's even, in the really sophisticated ones, they have mini processors in there, right, running the firmware and the opcode. So there's a lot of potential for non-linearities to creep into the solution, and we need to test these non-linearities. I like this slide. I like the phrase. I kind of borrowed it from the automotive industry from years back, right? And I'm trying to say it's more relevant for us than ever. But there is no replacement for displacement. I just highlighted there's a lot of permutations that of multi-phase solutions to powering the vSynth in vSynth core for an AMD chip, and we need to wring that out because there's a lot of a lot of possibilities for error. And obviously, with these different profiles, there's just a lot of testing that has to happen. We need to test for non-linearities. In the next few slides, we'll be looking at methods for testing these non-linearities as well as basic sort of static current testing. But there is no replacement for displacement. You can't rely on simulations. I mean, they can tell you, they can help a lot, right? But at the end of the day, you can't release a product into the real world with in any kind of volume environment without actually having tested the PDN. Now, you can potentially test it with the target device, but you can never go beyond what the target device can power. And if you're looking to design some margin into your power supply, then you need to test. You need to test beyond what the device can actually draw. And ideally, you'd be able to slew faster than the device can actually slew. And that gives you the design margin that you require to feel confident about getting your design getting it to market in a satisfactory production worthy condition. So this slide is again provided based on the Xilinx Versal AI family, and you can see here that we've highlighted 4 rails here. They're in yellow, and what we're testing here. So this is based on some customer feedback we've had. These are the critical rails to test. What we're testing with our FFED is these 4 rails because these are the most important to be tested in terms of transient load. And you'll see in later slides that we have other solutions that can augment the FFED, and you'll be able to test all the other rails. Because as we all know, look at how many rails there are in this representative example of the this block diagram. Okay, what does this mean? The challenge here really is more rails, more expensive development, right? And because the ROC is critical, the return on investment, I think it always, as historically, this always gets pushed down onto the design engineer or the validation engineer on how to fix this in a faster time. So really, I think the 4th challenge here is how to do more testing in less time and feel more confident about your design. And we'll talk about that in just a moment. So I'm going to move to slide 8 now, which is the last of the challenges that we're highlighting today, and this is what we call consistent measurement points. And I kind of mention this because it's been prevalent since I sort of first walked into a lab after college, and we spent with 2 different development sites in different geos and time zones, and we were just trying to get a baseline measurement on a PCB, because we were trying to power a chip. And just to get that baseline measurement took quite a lot of time because we were using different equipment and different techniques for measuring. And we'd had this conversation about where should we be measuring. So what you can see here on the slide is a cutaway. It's a 3D cutaway of one of our passive adapters that's used on one of the Xilinx solutions we provide. And this is you'll see it in greater context in a couple of slides. But consistent, it's not just like it's getting consistent measurement, and then you can agree or disagree with whether that measurement is correct, or do you need to do anything about it. But just actually establishing a baseline and agreeing on that can be quite consuming in itself. So I'm just going to review the problem statement. Unknown load profiles, increased current, and I guess with increased current is the need for more phases. More phases is more non-linearities. If you think about, as the phases are added from the power management solution, they're further and further away from the actual device you're powering. So the phases on the outside, on the outer, if you're looking down on the board from the left and the right-hand side, they're at different lengths than the ones in the middle. So they probably have different trace inductance, power plane inductance, and series resistance associated with those. So they're going to, by definition, have different thresholds for when they need to be activated and not activated. You think about these solutions, as you add a phase or remove a phase, when the current goes up and down, these phases are shared on. There's diode emulation, and there's power saving techniques that every architecture implements. And of course, every vendor has slightly different ways of implementing these architectures. So there's different things we need to be looking out for, and we don't know quite how exactly they're going to react. So the increased current offers a lot of potential for some peculiar corner case activity that we're not going to be aware of until you actually get that product and you're actually slamming the rails itself. As we go down in geometry, as the functionality of these devices increases and the gate voltage goes down and the vSynth or the vCore voltage goes down, then the regulation is tighter, right? If the voltage goes too high, you can damage the device. If the voltage goes too low, then you have a signal integrity issue. You could lose the data. You could have a data integrity issue, more importantly. And that obviously is, that's what we're here for. That's why we've all got jobs in power management and making sure that these devices go to market tested on the system boards. And then last but not least, how to measure, where to measure. When it comes to the Xilinx devices, we're okay because there's a clearly defined place on where to measure. And you'll see in the products I'm going to show you now that we have the same test place locations that have been determined by Xilinx ahead of time. So when it comes to the Xilinx solutions that we offer, you'll see that all that kind of those important measurement points have been defined ahead of time. And if you look closely on the passive solution at the top left, in this slide, there's three main areas. The top left-hand side is the passive passive solution. And it consists of a slammer, which is essentially a handheld slammer. And then the adapters are in the middle. There's two adapters. It's the same adapter, but one's upside down. And you can see the upside down one at the top is a BGA. So that would be reflowed down onto the device you're testing, the DUT. And then just in the interest of being able to see what's going on, you can see that the bottom version, the passive adapter is turned upside down, or turned right side up, should I say, and you can see the connectors. So you can see that there's a lot of connectors on there, and that's so you can have access to all the various rails that you can test. And the large connectors there's a large Samtec HSEC 130 and some smaller ones scattered around, and those are for slamming the various rails on the solution. With the passive solution, there's also a remote sense cable. So that's, you can see there's some SMPs on the passive adapter, those gold round circular connectors, and those are what the remote sense connects to from the handheld Pro 1000 RS in this example. Just to the right, there's some smaller versions. It's kind of like the size of a large matchbox or something like that. If you need to do continuous current or OCP testing, then you'd add what we call the PTO, which is the red and the black cube on it. And then you can see some cable tips at the end that would plug into that. And that allows you to connect the top of the passive module to an electronic load in your lab. So you can do additional constant current testing as well, so stress testing your OCP or just getting a basic efficiency measurement. Underneath is what we're really just releasing right now, which is the FFED test solution. We call the FFED as an acronym. It's short for form factor equivalent device. And that is basically, as the name alludes to, it's a form factor equivalent device. I'm going to zoom in on it in another picture. The big difference between the passive and the active solution, or FFED, is the amount of testing you can get done, and that's the automated testing that is featured in the product. With the passive, you have to, between each rail, you have to set up a new test and remove the slammer and put it into a new connector and possibly move the measurement points on the passive adapter. But on the active, it's all automated through that pod in the middle. That's what we call the X pod. And then on the right-hand side is the ORAC, or what we refer to as the brain. And that's basically sending the test measurement vectors and recording the results from that. In the next slide, there's a comparison table here. So as Bill said, you'll be able to download this presentation after the fact and look at this comparison slide. But of course, all this material is on our website as well. As I say, as questions trickle through, whether it be now or later, please just drop us a line. We love talking to customers. It's how we make sure that we're developing the right products and making sure our roadmap aligns with what our customer needs are. So there's a zoom in on what's going on with the FFED, and really the purpose of this is to highlight the fact that it's X by Y is the same, but also the Z. So the height of the package is the same, and critical to this slide and the previous slide is to understand that the FFED does all the power dissipation in the device. So if we go back to slide 10 real quick, you can see there's a thin, on the bottom left-hand corner, there's the FFED, which is the copper lidded device. Between that and the X-pod is a cable. That cable is just for just measurement and vectors. There's no power going through that. All the power that's being dissipated with the FFED is through the lid of the device. And if you can see bottom right-hand corner of this slide, it says load cells embedded in active module. So that means you can do thermal emulation as well. And you can test your system from a thermal, you can test your heat sink, but also you can just test the overall thermal performance of your system as well. And that is obviously more and more relevant in this day and age. That is, I think that's all I need to cover on that. I guess the other thing is, yeah, there's a lot more functionality. We're testing the rails with the load cells, and they're closer to the socket or to the, in this case, the LGA pad or the LAN pad of the DUT that you've developed. So our DIDT can be much faster. So you've got much more greater possibility. You can stress test your DIDTs, your excursions, more rigorously with this down solution, if you will. Okay, so this is kind of a zoom in on it, and that's what we're going to be using in the demo in just a minute when I turn this over to my colleague, who will be walking us through the demo. Okay, so on the left-hand side, you've got this form factor equivalent device dissipating the heat. If there was no heat sink on this product, then there's thermal sensing, protection involved, embedded into the FFED. And if there's no thermal solution, you're not going to be able to do much testing. That's the result of that. Okay, so I'm going to turn it over to my colleague in the lab here.
Thank you, Roger. Now that we've connected all of our devices to our test setup, we are now going to begin configuring our test settings. Here we have an example of the power map for the VC1902 platform using the values pulled from the Power Design Manager, as well as margin to stress test the device under test. For this example, we will only be using one rail. So we will right-click within the window, deselect all, and click on the rail we want to use. Then we will move on to our pass-fail settings for the sweep. Here we can see all the values that will be used for our pass-fail settings. Any of these values can be changed by double-clicking within the box, but for now, we will leave these as default. Now we configure our static load settings for the sweep. Here we will get a visual representation of what is going to happen using the settings below. By clicking any of the values, we can edit the value or the formula within. For this example, we're going to use steps of 25% rather than the default 5%, and use a duration of 5 seconds rather than the default 10 seconds. Finally, we'll move on to our dynamic settings for the sweep. All of the settings can be seen in the table below, similar to the static load. Any of these values can be edited by clicking on the value. For now, we're only going to change the duration formula from 1 second to 100 milliseconds. Now, we can go on to Run Test tab and begin the run. Now that our test is running, we can see above on the GUI that we're capturing the voltage and current waveforms. If we zoom out all the way, we can see the full 2.5 millisecond capture that the GUI is able to do. At any time, we can pause and zoom in on any axis to be able to see what's happening. If we press stop, we can stop the entire test, which then has to be restarted from the beginning. This is essential if a critical error is seen during the test. Now that we've completed our 118 tests, we're now going to view our results. Within the Reports tab, we can either view the results, create a detailed report, or export all of our data to CSV. Within the detailed report, a name is required at minimum, but we can also add a board serial number, a bench number, as well as display top, display base, overshoot, undershoot, and waveform. These boxes will add significant amounts to the PDF and much more time to generate, and so for now, we will leave it simple. For this one rail, we've generated 15 pages. Here's our welcome page, the table of contents, a summary of the pass, borderline, and fail. Borderline is anything within 10% of failing. Below that, we can see our tolerances for the rail. We can see our dynamic and static load settings. If we continue to scroll down, we can see the VCC int, our first rail, broken up into a dynamic and static load for pass, borderline, and fail. Continuing to scroll down, we can see more details for our dynamic analysis. We can see the 25, 50, and 75% graphed here. And below, we can see the table that corresponds with this. And within the table, anything white or gray is passing, anything orange is marginal, anything that is red is failing. Scrolling down, we get to our static data. Here, we can see our static data represented in a graph. Below that, we can see the table that corresponds with this data. If we decide we wanted to do a single test, we can go back to Run Test, go to Custom. Here we can set the test type for either static or dynamic. First we'll set it for static, and we can see our settings below. Here we have the current we'd like to use, as well as a preview of the current. If we press slam, the current will begin the slam.
The GUI will only capture a 2.5 millisecond window of the slam.
The slam is continuing until you press stop. If we change the test type to dynamic, we can see all the dynamic test settings below. And by pressing slam, we can get the data that we wish. Now that we've completed that testing, let us move on to a 3D plot using voltage, frequency, and duty cycle. Here we can see the data is generated in real time once we've pressed run. And we have an index below letting us know if the slam was a pass, marginal, or fail. Thank you for your time, everyone, and I hope you enjoyed our demonstration. Now back to you, Roger.
Okay, thanks, Rob. This is my favorite slide. And it's kind of glad Rob finished at the right time, because this is the slide I wanted to talk about. We talked a lot about non-linearities and these pseudo-random events that can happen because of a multi-phase solution, which is only exacerbated with random or pseudo-random profiles, load current profiles. So there's two major tests that we perform to spot weaknesses in a power supply or a PDN quickly, whether it be the controller or the caps or whatever it is down the PDN. And the first one is where you sweep, as Rob did in that very brief demo. We sweep duty cycle. We basically have a voltage controlled current sink, which is what our LoadSlammer is, which is in the FFED or in the passive solution. and that voltage control current sink varies it can vary the rise and fall time. It can vary the destination current, and it can vary the duty cycle and the frequency of the pulse as well. So that's a lot of permutations. So a great way to quickly spot weirdness, for lack of a better word, or abnormalities, is to do a 3D sweep of duty cycle and frequency. And you think about a regulator. We previously discussed that you're going to have to test a lot of times with one pulse just to make sure you find the weakness of your PDN. But in addition, it's a function of the DIDT, or the slew rate, right, of the rise time of your pulse, and the length of the pulse, and the distance between pulses, because there's a time constant associated with the inductor and the capacitor and the switching frequency. So there will be a place where the regulator performs better and a place where the regulator does not perform as well. So you have to identify that along with the area of where you are in the slamming cycle relative to the power supply. So that's a lot of testing. So you can do a 3D sweep. This is a 3D sweep of duty cycle and frequency. And it's not flat. Like in an ideal world, it would be flat. Or would it? Because with these high current devices, we have load line, okay? And load line has been designed to help us meet regulation. So as the current output goes up, the target voltage goes down. So this is a function. What you see here is a function of load line, but it's also, the load line is varying with duty cycle as well. Is that correct? I don't know. But the point is, you now know that it's something that somebody needs to address. Hopefully your power management vendor can help you work through that. Maybe this is correct. Obviously, there's a time constant associated with load line. I mean, what is the bandwidth? And of course, that's going to vary based on some register setting somewhere in the controller. But should it vary as a function of duty cycle? I don't know. I'm going to let you find that out from somebody else. But this is a great way to do a lot of testing very quickly and visualize it. As you can imagine, it's quite easy with this level of automation in the GUI to get a lot of data, and then you got to sift through it. And we will talk about that in a minute. But this is one of my favorite plots, one of the best test features on the product. The other great test I like is the large signal output impedance, and this is where we sweep a sine wave, a large signal current in a sine wave, and we sweep it through the frequency domain and look and see how the impedance varies as a function of frequency, and we get to adjust the amplitude of the sine wave and the offset. So that in itself is a whole new set of conversations and is a whole new topic. But it's another fast way to identify fundamental weaknesses or areas that may need to be focused on in greater level of. So I don't think we don't have the large signal output impedance. If you want, we can do it. Ask for a demo on the website, and we can do a large signal output impedance for you. I'm going to move to slide 15, which is. This is really kind of where the test engineer leaves. With Xilinx, you would have your PDM, the Power Design Manager tool, and that would tell you, like it did in a previous slide of us, on how much current you can expect to be pulling from the device, given the the amount of utilization and clock frequencies, etc., that you're going to target the fabric with. That's kind of a conversation you have with your Verilog system engineers. Here's like where you enter those coordinates into our tool, and this is where it sets the pass and fail and the margin criteria. So that's kind of like, that's where you essentially develop your test vectors for your testing of this device. So and there's also, you set the margin. You're going to see the margin in a few more slides. You'll see the marginality, right? So a lot of feedback has been, okay, that's cool, it's a pass, it's a fail, but where does it get close to a fail? Because that's where we want to hone in on that, and see what that is, because quite often that's where it's going to allude to what if there is a problem, like a time constant problem, that's going to allude to where that is, that marginality. So the marginality is also configurable through this input stage. Okay, so here we are. This is the static load that Rob went through very quickly in the interest of time. And basically, he's stepping through, I don't know, what's that, 10, I'm not going to count them, but 10, 15 steps from 0 to whatever, 200, 190. This is where you test. You can test for efficiency and also just ratchet up the thermal performance. If you're using the FFED, remember all the power is being dissipated through the lid. So we can slowly walk up the power curve and the thermal curve and see how our system is performing. Is the cooling solution working as desired? Do we need to increase the fan speed if that's appropriate, if that's relevant? But this is, and of course, the other thing about this is that you can now test the OCP. You can test the static OCP threshold. And of course, if you use the pulse, you could test the duty cycle. You could change the on time of a current pulse to test the dynamic OCP of your power system as well. This slide is really, as Rob did tear through the GUI quite quickly, this is really just a zoom in on a couple on the dynamic shot here, and it enables us really, you spot a problem, you can then go back and just identify what those use cases of where the problem was or the marginal results were, and you can just plug those back into the GUI and hammer out do a lot more testing in that specific area without having to go through the whole test suite again. And you can see, I think on the left-hand side, Rob alluded to, you can choose min, max, and the usual kind of like data capture options you need in a piece of test and measurement equipment. This is when we're doing a duty cycle sweep. And remember how you have to capture a lot of pulses, repetitive pulses, to find a weakness or find the weak point of a regulator. So this is basically him pausing and zooming in on a capture, whether it be just to prove that it's okay, or he may have found something that is of interest. We do have a number of demo boards in the lab, and we deliberately keep them untuned because there's all sorts of cool oscillations and weird stuff you can capture. So we're in the business of not optimizing the PDN just so that you can demonstrate what the tool can capture and what it doesn't capture. This one is this is where we were talking about the load line earlier, and this is the load line in effect with a sweep. I don't know, done 118 tests on this, and I think you can pause on this and zoom in and see what's really going on. As I say, if this is a custom board a customer board that has been optimized, but we have a number of demo boards that are not optimized. But this one is using the FFED for Xilinx, so that's why we're showing these results. And that's why Rob was using running that GUI in the lab just now. But it's pretty fun looking at all the weird oscillations you can see. Okay, I'm going to move to the next slide here, which is this is a picture of a number of different pages from a test report. You capture a lot of data. I think the test report we have a demo or a downloadable sample test report on the website. And there's, I don't know, 550 pages of stuff there. There's a lot of data, and you can choose what you want to see and what you don't want to see, because once you flick through a few reports of 550 pages, you probably only want to see the summary. So what we've spent a lot of time on with the GUI is making sure that we're summarizing, the pass, the fails, and the marginality of the of the tests that have just been run. All this stuff can be recalled as well, so the data is always stored and the test vectors are always stored. But this testing really, you know, we pride ourselves on listening to the customers and providing what is required to get you to market faster. But we're not clairvoyant. And what I mean by that is that we don't know what other bench equipment you have in your lab. So recent feedback has been, you know, great. The automation is fabulous. Thank you. But we need to integrate it with an oven. We need to integrate it with an oscilloscope, a third-party oscilloscope, because obviously you can measure, use our ADCs and DACs inside our own test equipment, but it's good to also verify that with your own bench equipment. Obviously, everything we send out is calibrated and measured, and there's a, you know, an annual calibration. But you want to be able to coordinate it with an oscilloscope because you might want to take a measurement somewhere else on the board. You know, you're busy debugging other elements of the board, right? So you want to be able to get a trigger from us and trigger an external oscilloscope. You want to be able to sequence an oven, do some oven testing, and or some, you know, variant bench supply, which is powering the input to your power supply. You want to be able to sweep that so you get some margin. How can you do corner testing without putting your system through the corners? Spent quite a bit of time developing an API which works in conjunction with our GUI. So you can plug in all your favorite bits of bench equipment, which is going to be necessary because the amount of testing is large. To feel confident about getting a high current device out into the market with the optimized PDN and feeling confident about the integrity, the data, the power integrity, and consequently the data integrity of the solution. 21 is basically you can see all this on the website, but it's an overview of the type of products we have, and it's all based on getting customers to market faster, making you feel more confident in your design. Consistent measurements. On the left-hand side is our latest controller. It's called ORAC, which I think is short for Oracle. But the ORAC controller is able to do multi-rail slamming simultaneously, so that you can test for cross-regulation, so that if one rail suddenly gets hit, does it affect another rail? And then you can stack these guys as parallel them, so they will time synchronous, so you can do concurrent slamming and measurements on as many rails as you want. And all this is on the website. We've just done a big restock with Mousers, so you can go onto our website, and then it'll point you onto the associated products with Mousers. So all those, the latest Xilinx devices are all the passive adapters, and soon to be FFEDs will be on that. So you can just find out, you know, if you've got questions. It's all pretty straightforward. This is a website. This is a picture of us going from, you know, this is on the AMD Xilinx website, and this is pointing to our new Xilinx landing page on the LoadSlammer site. So this is part of the Power Delivery Tools landing page on the Xilinx website, and it points to our new page, which is here. And there's a lot more information about what's available, and again, the test reports and the data sheets and all that good stuff, and how to buy it. I think that's all I wanted to cover. Bill?
Okay. Well, we have a number of questions here.
Oh, good.
So we'll jump right in.
Sure.
If you have a question, you can submit it by typing it into the Ask a Question box and then hitting the send button. Also, please take a moment to complete the feedback form, which will appear on your screen at the end of the webinar. So to start with, is there a way for the FFED to compare the GUI and oscilloscope measurements?
Yeah, that's a good question. The short answer is yes. And there's hooks on the top of the controllers that connect. They have an SMB connector, and you can go from there to an external scope. In fact, that's how we calibrate and validate the equipment before it ships out. We use the same portal there for testing the output before shipment. And there's a second connector for the current measurement as well, so that you can validate the current size and the slew rate, as well as the voltage of the sense points.
Oh, very good. You mentioned the API support. Will this include Python?
Yeah, so I'm not a programming expert, but my understanding is that you can send commands from the usual cast of characters of languages, including C, C#, Python, and you can send a command from your language of choice to a shared DLL that will then operate the GUI, which is so you're talking straight to the GUI through an API, and you can use Python or any of the usual languages. There's also a command line interface as well, like the old school command line interfaces. So you can do a scripting type of event through that as well.
Okay. How do you determine the slew rate to use per
Yeah, that's a good one. This is a great question. It's a seminar in itself, okay? But there is the rule of thumb that is that Xilinx provides for. If we're talking about a Xilinx device, there are some guidelines that Xilinx offers on their devices, and there's two guidelines. There's a slew rate, and then there's, I guess you could turn that into a rise time as well if you've figured out what your worst case event peak current is through the PDM, or you can use. There's also a frequency domain analysis that you can get that information from Xilinx as well. And that in itself is, that's a good conversation, because what we're really talking about is what can the power management solution, the PDN, deliver before the package gets in the way of that transient performance. And that's a great question, and it can be the models can be you can get the models out of Xilinx, if you've got using another large digital ASIC from someone else. The trick is to understand the power bandwidth of the package, not the bandwidth, but the power bandwidth, and it's that is the trick to ascertaining the slew rate of what you need to be testing to. I don't know if I answered that question. Did I answer that question?
I think so.
Okay.
All right. For the next one here, could you explain the DC load connection again?
Yeah. So in the, can I change slides? Is that okay to do that?
Sure.
Yeah. In this example here, with a passive solution, you connect what we call a PTO, power takeoff unit, and that plugs into the large SAMTech connector, and you can connect that to an E load. And that's what you do with a passive solution. If you have an active solution, you just turn up the DC load that you want, and it dissipates it through the active load cells. So so in this example here, the power comes out of the lid of the FFED in the form of heat, right? So you want more DC, it dissipates more heat. So you just need a better cooling solution. If you want to do more DC, but you're you don't have a down solution like the FFED, you can put down a passive solution, and you can see in the middle, there's these large, you can't see my cursor, can you?
No.
Okay, so if you can see that there's one device just to the left of middle with two rectangular connectors on it, and those rectangular connectors can plug a slammer into them, or you can plug a PTO, which takes the DC load off to an E load, and you can plug the slammer in on top of that, so you can do your AC and DC transient testing like that. And then there's also a PTO on the right-hand side. There's a 3x2 grid array of cubes, which is a 360 amp PTO. And you can actually, these PTOs are designed to really you can just solder them across caps on a board. They're really they're just good pieces of lab equipment, really. You can, they're designed to, if you look at any large or medium-sized power delivery network, there's going to be a cluster of caps in parallel. And these PTOs and protectors are designed to just solder across those. There's a little video on our website about how to do that, but it's great, just lab equipment. You can just tack these on and draw a current quite easily without having to do any invasive rework. You can just tack these on top of a bunch of decoupling caps.
Got it. Could you tell me more about the GUI telemetry support?
Yeah, that's we didn't really cover telemetry at all. I apologize for that. We do have what we call the blaster, or the master blaster. It's in this picture here at the bottom, and that is we have most of the protocols available in the market, including the sort of proprietary ones by AMD and Intel, and basically you can plug that blaster in and capture telemetry from a power management device, and you can also write to the power management device as well through that blaster. And the API ties the blaster into the GUI so that all the telemetry data is captured. Now, telemetry data isn't that fast typically with a power supply. You know, the ADC data isn't that fast, so it's good for DC measurement, but and for thermal reading data back from the regulators in terms of thermal performance. And yeah, and then you can set the OCP and that sort of thing. And you can read and write via the API, or there's a standalone telemetry GUI you can use.
Okay. How do you compensate for the inductance of the interface from the LoadSlammer test module to the tested printed circuit board?
So it depends on what the requirement is from the vendor. Okay, so in respect to these Xilinx devices, we know that they want to measure at the balls, you know, a certain specific set of balls. The short answer is there's a lot of simulation. And in fact, if you want to get the most accurate results, you need to simulate the dot in conjunction with the FFED or passive module. But we don't compensate necessarily for, there's not much of a difference. It doesn't really affect the DIDT. The biggest DIDT is not, the biggest source of error is not that interface. Well, it depends on what you're talking about, but the interface and where you're measuring. But we are measuring at the balls, and there's no current, you know, we're using a differential sense through a non-power carrying pair of connectivity with respect to the larger rails. So we have a sense point on the PDN, the dot where the PDN is meant to be measured with Xilinx. Other customers, other chip vendors have different sources of measurement and requirements, and we sort of account for that with conversations with those vendors.
All right. Do you have LoadSlammer support for other families of CPUs, SoCs, etc.?
Yeah, absolutely. We do the larger the device, we probably have it covered already, or we are working with that ASIC chip manufacturer. Yeah, yeah, and so the top 6 people we're typically working with, and then there's a few smaller startup companies that we're building solutions for.
You mentioned a number of phases in the terms of the current being delivered, like 25 to 30 amps per phase. How do you know the real number of phases?
We don't. We know the system engineer should know the physical number of phases, but we don't know how, and I think that's my point about the non-linearities, is that you don't know how many phases are operating at a specific time, because either they haven't switched on or not, or we don't know how many phases operate at what static current. So the answer is we don't. You know how many physically are there on the board because somebody's laid them out, whether they be in the modules or in a discrete solution. But from a testing point, you don't. And that's kind of like part of why you have to be so thorough. And you need these, large signal output impedance and 3D sweeps to establish a baseline of what's going on your board. Yeah, it's a good question. Yeah, you don't.
Okay. Many BGA packages provide a level of thermal conductivity through the balls. How does the FFED replicate this? Having all the power dissipated through the lid may not be an accurate representation of the overall cooling solution.
That is a fair statement. And what we do is we can offer, our simulation and our measurements to show you how much is going through the lid versus what's going through the balls.
Okay. Can you do a 3D plot with slew rate as one of the variables?
You can in the next release of the GUI. Yes. So you can change the variables of the 3D sweep in the next release of the GUI. Yeah. Okay. And one thing we haven't really talked about is the DIDT, the slew rates of our active cells. But we have, devices that can go. We can slew in 7 nanosecond rise time, like a full-on rail at 7 nanoseconds. But the question is, can the power or the current be delivered in that time? And the answer is invariably no. But we have, we've done a lot of die-level emulation testing for certain customers, so we can do that in as well. But that whole slew rate rise time can be configured in the GUI. Now, I'm not saying that the Xilinx devices, we don't test those to 7 nanoseconds rise time, but I'm just saying that there is that possibility generally.
Okay. I saw a reference to continuous static load transient testing on slide number 10. It seems the limitation of testing is due to the FFED load cells. Could you elaborate further on this?
Yeah, there's always going to be a limit on what the load cells can test. Absolutely. And it comes down to what we can pack into the device versus what the target device that we're trying to test for can handle. So at the moment, we're ahead. Our power density is ahead of the chip that we're testing. And with some margin, we need margin, right? Because we need to test for OCP and just give the designer, the validation engineer, more design margin. So that is a limitation with the active solution. If we weren't able to dissipate more power or more current than what is required, but we are, and significantly more at this point in time. And a faster edge rate. But the whole point of this testing is that we should be able to test the chip beyond its characteristics that it's going to need with respect to rise time, peak current, and power and thermal.
Okay. Is it possible to power the FPGA devices like an UltraScale Plus at quote-unquote distance? For example, if the regulator is outside the FPGA board, potentially connected to the FPGA board through a 30 to 50 meter cable?
No, I don't think so. I'm pretty confident you can't. And well, it depends on where the power regulators are. Where the point of load of the regulators are, right? Where are they in relation to the device? But there's one way to find out, and that would be to test it with one of our solutions. But not 30 to 50 meters. I don't think so, unless if the power solution is needs to be next to the device within a few inches.
Okay. Where is the voltage sense point with the FFED approach?
It's per the data sheet in respect to the Xilinx devices. It's per the data sheet where they say you need to measure. It's on a pair of balls underneath, which is the kind of the datum point for the voltage for vSync.
All right. Well, I'm afraid we've run out of time for those questions we didn't get time to answer. We'll get back to you via email. This concludes today's presentation. On behalf of Electronic Design, I'd like to thank Roger for a great presentation, Programalog for sponsoring today's event, and of course to all of you for joining us. Have a great rest of the day.
Appreciate it. Thanks, everyone. Bye. I look forward to your questions.